Performance, ladies and gentlemen, is not just a technical detail. It's the difference between your business being proactive and reactive. Imagine those missed sales opportunities on the big sales day when your application couldn't scale up. Or imagine detecting frauds after the fraud has happened and not before. So designing for performance, especially when it comes to data systems, is really crucial for your business to make the right decision at the right time with the right insights. My name is Sandeepan Bhaumik. I'm a Principal Analytics Solutions Architect at AWS. And today with me, I've got Scott and Kamal, who will be co-presenting. They will introduce themselves when they come up on the stage. So what are we going to cover? We'll start by defining some mental models around designing for performance. Then we'll talk about 3 use cases, common problems that we hear from customers when it comes to achieving optimum performance from data systems. And we will support that with 3 solution patterns that we have implemented for customers. And one of them will be shared by Kamal, who have done them in the production. I will then close the session sharing some thought process around how you can think about performance optimization when it comes to data workloads, and then leave you with some thoughts on what you could do next. We have a lot to cover, so let's get started. Now, we have all been there. You run a query and keep waiting for it to return the results. Or you run a report, keep waiting for it to load. When it takes time, and when you get the result, you see that the data that you're expecting is not available. The latest data has not arrived yet. And that diminishes trust on the data systems. People lose confidence on data, and they stop using these systems. And on the other hand, you have got systems that cannot scale, and with load, they create bottlenecks. And these bottlenecks not only creates a bad experience for the user, but it overburdens IT with firefighting issues. That's why it's critical to have that performance lens in mind when you design these systems. It's not straightforward, but let me share some mental models on how you can think about them. The way I see it is through this performance pentagon mental model, balancing 5 critical factors: latency, the ability to process data faster and deliver data faster; scalability, the ability for systems to keep up with the user load, to scale up when the demand rises in peak times, and then scale down when there is no demand so that you can save on costs. That without compromising on the latency requirements. And then efficiency. How efficient are these systems? Are you maximizing resource utilization while keeping costs low? Reliability. How are you designing for failure? What happens when something breaks? Can you abstract that away from the user experience? Can you recover systems quickly and fast enough? And most important, cost. How can you minimize cost when you design these systems? You see, you can have sub-second latency on data systems, but that can drive costs up. So you have to make a trade-off. It's a trade-off game. You have to find a sweet spot. And what I see with businesses is how you can achieve that within that green area in the middle. Making trade-offs and making these decisions is crucial when you put the performance lens on your data workloads. How to do that? Let's look at some real examples. We will start with a high-level conceptual design of a data system that demands high performance. Imagine a retail business with both physical stores, bricks and mortars, and an online store. Now, in such a system, you will have different kinds of users using the data from these systems. You would have human users who would run reports, run queries on the system, or think about store managers who would rely on inventory, stock data. They need the data right there when they want to look into it. They cannot rely on old data to make inventory decisions. Or think about customers who have made a payment and want the confirmation that the payment has been made and want to look at metrics, last orders, what they've ordered previously, stuff like that. These human users need data when they need them, when they require them. And then you have got systems, non-human users, automated notification systems, agentic workflows that will demand the data when the data gets generated with lowest latency. Think about detecting fraud before the fraud has happened. So these are like real-time intelligence systems that you need to build with high-performance data system. Now, what I want you to take away from this architecture is the core components of a data system. You have the consumption layer on the left-hand side. You could have microservices built for serving different capabilities from a website or from web application. And then you have the storage layer with different kinds of storage systems. It could be a database, a data warehouse, a blob storage, each of them with different internal architecture. And that means you have to make different decisions on best practices. You have to make different decisions on that pentagon, balancing those critical factors. Then we have got this data processing service, which needs to process data faster and scale as data grows. That on data that has got large volumes of data and data traveling at various speeds, either in batch or real time. And then the ingestion system, your data collection system, connecting to different sources, systems with different formats and sizes of data, and bringing them together and feeding that into the processing service. Now, the way to think about performance when you look at the whole architecture is focusing on each of these components and putting that pentagon model on top of it and seeing how you can balance those critical factors in each of these areas. Now, let's look at a real-life example. This is one of the use cases, a very common use cases that we talk to customers about, highly concurrent workloads. And this is on the consumption side. I'm talking about users running hundreds and thousands of queries on the system, which can easily take the system down with that kind of load. And these queries are of different patterns. You will have users running long queries, complex joins across multiple tables on huge volume of data. You will have users running short queries, interactive queries, ad hoc queries. You will have users running aggregations, running queries on white tables, right? And then they need low latency. They want to see the latest data on these kind of systems. Now, the way to think about building solutions for these systems is that there is no one service fits all. You have to attend to different query patterns. You have to attend to peaks and troughs. You have to think about how to manage with microservices. Microservices, while they are really good in architectures, they can add complexities. You can have different data systems at the background. So it's important to choose purpose-built services for these kind of solutions. This is an example, a pattern of a solution that you can implement for highly concurrent workloads. So you can have users coming in with different requirements, running queries on usage service, health monitoring service, or even doing trend analytics, etc. Now, when they run these kind of queries, these are of different patterns. The experience that you can give your users is abstract away the decision-making of where they should run the queries. And this is where this query API service comes in. So you build this query API service, which takes these query workloads from the users, explores the plan of the query, and decides where this query should run. Complex query with low latency requirements, joining multiple tables, scanning data across multiple years. You can run them on Amazon Redshift. Amazon Redshift is built for those kind of queries. Provides sub-second latency on these kind of workloads. Interactive queries, running ad hoc queries and stuff like that, you can think about using Amazon Athena. Now, these are just two examples that we are using. You can think about the different query services available in the market that can attend to this kind of architecture. And these systems can scale independently. They can scale up and down depending on where the load rises. On the other hand, on the left-hand side, you have got storage systems. So Amazon S3 is the object storage that we have got where customers build data lakes. Now you can start thinking about how to implement Apache Iceberg, open table formats. These open table formats come with built-in architecture to improve performance. For example, Iceberg optimizes read queries through partition pruning. It uses file-level metadata to improve query scanning on top of the data. And it supports atomic transactions, which means when you do the data processing and insertion on the data lake, you can do incremental updates and deletes on top of the data lake itself. It improves performance because you can now make decisions across that pentagon on where to scale, how to keep cost minimum, how to achieve latency, et cetera. And then another advantage is the integration with our metadata store, AWS Glue, on top of Iceberg, so that all of these systems can connect to the data catalog, and you can organize your data and manage security at the catalog level. Now, Scott, can you talk to what you talk to customers about Amazon Redshift and Athena when it comes to performance?
Absolutely. Thanks, Andy, and thanks for joining us this morning. My name is Scott Rigney. I'm one of the product managers on the EMR, Glue, and Athena teams. And Sandy's question is a question I face or kind of see in my inbox or Slack on a pretty frequent basis. And that is, how do we, given an architecture like this, scale up our workloads to achieve high concurrency in query analytics? And so often this is, oops, we're on the wrong side there. So the reason for this discussion is obviously pretty interesting, right? So we want to scale our workloads so we're able to serve a variety of workloads with low latency. And one of the steps that we typically recommend to customers is by first taking pain to invest in optimizing the duration of your individual queries. The reason for that is intuitive, right? As you're able to reduce the duration of your queries, you're able to run more of them in a single unit of time. Challenges with that is that query optimization is a pretty difficult topic and pretty time requires a good amount of time to really get right. Thankfully, our services like Redshift, Serverless, and Athena are here to help with built-in features that help you reduce query runtime through some of their built-in features. Starting with Redshift Serverless, we have features like auto-materialized views. And what Redshift does with auto-materialized views is monitor your workloads over a range of different performance dimensions in order to determine when to materialize frequently accessed tables into a view, which will in turn accelerate subsequent queries on those views. Automatic table optimizations are another type of automated feature that Redshift provides. And what Redshift does here is automatically apply sort and distribution keys and other indexes on top of your tables to optimize the overall query patterns for tables in aggregate. Athena is a little bit different. So Athena also has many of these built-in optimizations as well, such as automated join reordering. And what Athena attempts to do with auto join reordering is, if it believes it can accelerate your query without impacting correctness, it will shuffle the order of the joins in your query plan. So that's a built-in feature that you get without having to sort of modify the queries that you're submitting to the Athena service. Athena also is different than Redshift, which in the sense that Athena does not have built-in storage, right? So unlike Redshift, which has the ability to apply indices on top of data that you're storing in Redshift, in Athena things work a little bit differently because you're typically using Amazon S3 to store your data lake files. So the choices that you make in your storage decisions can impact the types of optimizations that you get out of the Athena service. One example of that is with partition indexes and partition pruning. So these are features that if you're using Parquet, Athena can apply pretty sophisticated optimizations to reduce the amount of data scanned and read from S3 to minimize the latency, minimize query planning, and minimize other attributes of your query's execution. We've been hard at work this year building new features across all of our services. This is just a sample of the few that could come into play when we're building out our highly concurrent workloads with Redshift Serverless and Athena. One of those is query identifiers for Redshift Serverless. And what query identifiers give you is the ability to tag a query or workload and then monitor its performance over time. So ideally, you'll tag your queries, and be able to leverage automated table optimizations, auto-materialized views, things like this, to see your query runtime reduce over time. And in our low latency query scenario, we could also benefit from session reuse. And what session reuse provides you is the ability to quickly connect and disconnect and resume sessions on your Redshift serverless compute to minimize time spent retrieving data, thus accelerating the time to insights for your end users. On Athena, a lot of folks use Athena to query data that they're storing in S3, as we know, but going beyond that in transactional sources like Oracle. For this, we introduced a feature earlier this year called pass-through queries. And what pass-through queries provide you is the ability to push an entire query operation down to the source and read data from the source directly. So we've heard great things from customers in the amount of latency that they've been able to squeeze out of the system when using that. So now that we've been able to sort of optimize our individual queries by reducing their runtime, we still need to solve another problem that's important to our high concurrency workloads. So this is really the problem of variable workloads, right? A lot of us have kind of dealt with this one in our day-to-day kind of use cases. So here we have a mixture of steady state usage offset by periods of bursty, high demand activities, and a mixture of different sizes of queries. So huge jumbo queries depicted off to the very right of the slide, as well as some of our smaller dashboard queries that land earlier in the day. So we need to solve that problem, and one way that Redshift Serverless solves this problem is through AI-driven scaling. With it, Redshift automatically scales as your workloads change, giving you the ability to adapt flexibly. Redshift Serverless evaluates metrics such as data volume, number of concurrent users, and query complexity to help you maintain a price performance target. Our internal testing showed pretty significant results of a 10x price performance advantage when using the AI-driven scaling without really any tuning needed. Now, Athena is a little bit different, so we have to kind of take into account a couple different attributes when looking to scale our Athena workloads. Athena's queries by default run against a multi-tenant serverless fleet of capacity. And internally, Athena works to optimize the size and kind of composition of that capacity based on customer usage, right? So as you're sending queries to the Athena service itself is modifying its capacity pool. And it does that with the goal of minimizing query start time across all customers. But queries in your account will actually compete for your account level query quota. And so as you're scaling your workloads, you may run into a scenario where different business teams are experiencing slow performance or queries in a queued state for long durations. And so to get around this, we recommend a feature called provisioned capacity in Athena. And what provisioned capacity is serverless capacity that's dedicated to your account, and it's a capacity resource that you are able to fundamentally modify to scale your workloads. So we recommend provisioned capacity when you have high concurrency needs and require predictable performance that you get to control explicitly within your account. So with provisioned capacity, you create a reservation, and that is a kind of a bundle of capacity that you can assign to your work groups freely. And then you add or remove capacity units to scale with your workloads. Best yet, Athena, this provision capacity feature is the same query engine underneath, and it's the same query submission model, so your end users don't need to modify their queries themselves, and they can just get started. And to scale our reservations, we can leverage built-in features through CloudWatch to monitor utilization metrics, to build reactive systems using Lambda and step functions, and implement custom scaling logic within our applications. So, Sandy, back to you.
Thank you, Scott. So, use case 2, real-time intelligence, another common problems the customers talk to us about. Now, this is about processing data and reacting to events in real time. It's not about scheduling jobs, right? You need to react to events. As they happen, you need to react. Think about fraud detection. I would rather say fraud prevention. How can you prevent frauds as transactions happen? How can you detect that? How can you process that data, send it to downstream systems? Now, this is continuous data processing, as well as you need an intelligent system that can dynamically adapt to these patterns. So you have a machine learning model, for example, that, yes, it is pre-trained with some knowledge, but it has to adapt to changing patterns in data so that it can detect new fraud patterns. Then you've got real-time reporting, operational analytics, right? People in the fraud detection team or prevention team, they would want to see what's happening right now. That's the data that's valuable to them. They're not interested in historical data. They want data, they want to see what's happening right now. And then you often have these non-human consumers to these systems. So in a fraud detection use case, you would have notification systems. You have some systems that make other kind of decisions and then pass that decision on to another system, right? So you need to think about how you can build event-driven pipelines that can react to events in real time and process huge volume of data in real time. Now, one of the common patterns that we see in these use cases is using an event-driven streaming pipeline. So starting from left, as you see transactions happening on an application, so think in e-commerce case, think about customers making financial transactions, right? Using credit cards and stuff like that. Now these events pass through the API gateway, and then there's a Lambda function that does some lightweight processing, cleans the data, structures the request payload, and sends it into a streaming buffer. Amazon managed service for Apache Kafka. It's a managed version that we provide for open source Kafka. It is a stream buffer. What that means is that it can bring in the event streams and store them, and then pass them to downstream systems. Downstream systems like Amazon managed service for Apache Flink. Apache Flink is responsible for processing this streaming data, making asynchronous calls to this intelligence system, for example, SageMaker machine learning models. So the request payload comes in through MSK, goes into MSF, Apache Flink. It makes a call with the request payload, sending the information to a machine learning model, which says, hey, this event looks like a fraud, sends the data back to Flink. Flink then structures the data. Depending on the downstream system, it can join onto reference data, enrich the event with more information, pass it on to MSK again, that decides how can it pass it on to different consumers. Now, consumers here can be notification systems using SNS to send emails, alerts to respective parties. It could be for real-time reporting using Amazon OpenSearch, for the operational analytics, for teams who want to know what's happening right now, look at dashboards and see what decisions they need to make. And then it could be for batch analytics. They send the data to S3, use Glue to structure the data, provide to your business intelligence team for wider analytics, or even make the data ready for machine learning training. So you keep the intelligence system training. So the key part of this architecture is this event-driven pipeline. MSK scales to hundreds of thousands of events per second. MSF can scale to hundreds and thousands of events by processing the data. What's important is these are serverless. Thinking about the Pentagon, it takes a lot of your effort to make those trade-offs and gives the responsibility to AWS. So we manage a lot of that for you so that you can focus on detecting frauds, for example. And these are all serverless, and these integrate together pretty well so that you manage them as a single system, a single pipeline, rather than having to manage different tools for different purposes. Scott, let's talk about OpenSearch and Glue. What do you talk to customers about when you talk about performance?
Absolutely. Thank you. So in our use case, as Sandy highlighted, we're using OpenSearch, and we're using OpenSearch serverless to deliver real-time intelligence and real-time insights on different data sources. One of the features that OpenSearch serverless provides is zero ETL and streaming integrations. This provides you a scalable, cost-effective way to get data into OpenSearch. And once data is ingested into OpenSearch, it can be indexed and queried at very low latency. Earlier this year, we launched integrations for S3, and DocumentDB and Amazon MSK to help you do that, right? So you're now able to pull more data into your OpenSearch clusters and serve insights at ultra low latency. OpenSearch has a built-in caching tier, which provides indexing and search compute caching. And the compute for that is measured in what we call an OpenSearch compute unit, or OCU. Previously, OCUs were consumed by indexing jobs, and the rate of consumption was primarily determined based on the size of the workload itself. With smart caching, we have now optimized the data management aspects of the indexing jobs so that we're keeping only the most likely to be used and most frequently accessed data in the cache. This helps you reduce your overall OCU consumption, making the indexing process a lot more efficient and cost-effective when providing data retrieval tasks. And then lastly, we've built out expanded capacity and auto-scaling features on OpenSearch this year as well. And that's going to help you scale your workloads on OpenSearch to larger and larger data sets. And we've done that by boosting the OCU capacity from a limit of 200 to 500 OCUs, and that's per account, per region. In our use case, we're also using Glue ETL to deliver batch data processing running on Spark jobs, and we're doing that to power downstream machine learning, training, and inference jobs. And to bring consistency in how those jobs execute, earlier this year we launched what we call Glue usage profiles. And usage profiles give you, it's one of those features where the name's kind of on the box, but it gives you a set of configurations and controls that let you define sort of the runtime boundaries of your jobs. And that's going to help you bring more consistent performance and control over performance and cost dimensions for those jobs. And to give you an example, you're able to now set the maximum number of workers or timeout for your job, and that's going to be helpful for us delivering timely insights for our business users downstream. And as you're scaling up the number of jobs in your system, we launched job run queues earlier this year. That gives you a fire and forget kind of developer experience where you're able to send jobs to the Glue service and have Glue sort of manage the queue for you. So that's going to save you time and effort in having to manage retries and try catch to handle any errors that arise due to service quotas. So with that, you simply start your jobs, and when your jobs would have failed due to a service quota limit, Glue will actually queue the job and execute them based on a first in, first out order. So, thanks.
Thank you, Scott. So, use case 3. Now, not every system or every consumer of a system would need data in real time. Think about consumers who would need exports or extracts of data, huge volume of data. Now, option 1 is you can provide the data to the customer on regular basis, on a scheduled basis, in a batch job, in batches. You can make this system more efficient if you have the customer extract the data on demand rather than you sending it over and over again. That utilizes resources better because you're not running the system again and again. Customer needs reports, ad hoc reports, they generate it when they need it. Self-serving analytics. And this happens with business intelligence reports as well. We see a lot of customers, yes, they look at standard pre-canned reports across their organization, but some of these teams need to customize these reports. They want to add more data. They want to add more columns. This is the problem that Workhuman solved for their customers. Ladies and gentlemen, let me welcome Director of Data Architecture, Kamal Sampath Kumar from Workhuman.
Good morning, all. Can you hear me okay? I'm pleased to be here at re:Invent. I'm excited to share the Workhuman success story with how do we enable self-service analytics to our customers. Before I go and talk about the solution, I want to give you a little bit of the introduction to Workhuman, who we are, what we do. We are global leaders in social recognition, and we are based in Dublin, Ireland, and Framingham in Boston. So what we do, we provide connected, human-centered workplace solutions to many organizations. Our platform supports three things to do. We help employees to thank each other. We help employees to celebrate each other. Celebration could be a life event, for example, work anniversary, or buying a house, or getting married. We also help our employees to talk to each other. Workhuman platform allows employees to recognize each other's contribution in real time through peer recognition. We do this through our cloud-based SaaS platform. Let me talk about some of the metrics that our platform deals with. We have 7 million users on our platform. Every 2 seconds, a recognition moment happens in our platform. What that means? It creates multiple touch points, multiple human connections. We have more than 100 million human connections in our platform. With this type of scale, it comes with its own challenge, the data challenges. For example, how we surface this data to a customer in a self-service way. You need to think from bottom up to have a foundational platform that allows you to pivot and adjust and deliver the consumption capabilities like Sandy talked about earlier. One of the strategy that we started with the data platform was how do we enable self-service capabilities for our customers? For example, how can we help users to make informed decisions through data? How can we help our customers to do reporting independently without the involvement of IT teams or engineering teams? How can we help our users to look into their data and understand trends and the patterns? For example, how much I'm spending for the next year in 2025. Data on its own has less value. Data to be productized, how can we do that at scale so that it delivers business value to the data, to the user? And overall, how do we reduce the operational overhead when users are dealing with the data? This platform, we built it 4 years back. We embarked on the journey using this as an underpinning principle. The architecture that I'm sharing here looks quite complex, but this is what we have built so far, and it's in production live, delivering capabilities to our end users. I will simplify this architecture into 4 key layers. We have an extraction layer which extracts the data from the source systems, and we do this depending upon the data type. And we have adapted several ingestion capabilities that are purpose-built for different types of source systems. We use DMS, Glue, and EMR, and combination of these technologies allows us to bring the data at speed into the platform. The second layer in our architecture is the curation layer. This layer acts as a cleansing layer, and also it secures the data. For example, how do you protect PII data? It catalogs the data that comes into the platform, provides a unified glossary for downstream applications to consume. The third layer in our system is the modeling layer. The modeling layer, this is where the magic happens. This is where all the transformation happens. The raw layer data gets transformed into actionable data product that consumption layer could consume and can deliver actionable insights to the users or downstream applications, and to power our product features as well. The last layer in our platform is consumption layer. I'm going to talk about this layer a little bit more briefly, and I go in detail a couple of solutions that we have built over that. This layer is responsible for delivering the data products that has been prepared and ready to be consumed for users and for our product. With that, I want to give an overview of a challenge that we came across. Our customers, we deal with Fortune 500 customers. They all have their enterprise platform, data platform. They want to ingest their data into their platform. But they don't want to interact with the SQL interface. They needed a dynamic data feed through an API interface on demand, just like interacting with the SQL interface, having a pass-through SQL parameters, query parameters, ordering class, etc. We took this as an opportunity and added a new consumption layer into our platform. And we call that as a data feed, data API. It created a B2B solution for our customers to directly integrate with Workhuman data platform to pull their data into their enterprise data warehouse. At a high level, the data feed generation is performed asynchronously. It has 3 distinct endpoints. How to request data, how to poll the data, whether the data set is prepared, and how to retrieve the data set. The design that I'm sharing here is for how to request the data set. As you can see from the design, we have used completely serverless technologies from AWS to build this flow. We have Cognito for authentication and authorization. We have API gateway for publishing and securing the API endpoints. We have Lambda, which accepts the request and processes the logic and delegates it to either Redshift serverless or Athena. Sandy touched based on that. Depending upon the complexity of the query, an evaluation happens by the Lambda function, and it routes the request. We store the status of the API in DynamoDB. And once the processing is succeeded, the data is unloaded to S3 bucket. The second endpoint here is once the data is prepared and ready to be consumed, it's then stored into S3 bucket. The request accepts, okay, based on the dataset ID, now I want to retrieve the data. Again, the flow validates the user identity, and API gateway validates the API request, and the Lambda function delegates it and finds out for this particular DB request, where can I locate the files? And the response is simple pre-signed URLs. And those responses are delivered to the endpoint as a response, and the customer downloads the data. With this solution, it made a profound impact for us because it created opportunities for, with having generic API set of interfaces that we have built, we can now publish multiple data products at ease. We don't have to go and rewrite. All we need to do is spend time in transforming the logic, transformation logic, but the infrastructure is there. The second solution that I want to talk about is how did we scale our reporting solution to thousands of users using QuickSight. Again, this solution is quite tricky to begin with because Sandy touched based on customers are using pre-canned reports, and that's the way our platform was. We were delivering pre-canned reports to our users, and they are not able to slice and dice the information with their own dimensions. They were struggling. They needed customization. They needed ability to do themselves and share it with their internal users. The challenge was, how do we do it at scale? And how do we bring that experience into our Workhuman platform? So we don't want users to navigate to QuickSight to do this thing. We wanted users to do within Workhuman's platform. We looked at QuickSight as a potential candidate for this to delivering the end-to-end solution. One of the key things that QuickSight offers is embedding dashboards. But we looked beyond that. How can we embed authoring experience? And QuickSight does do that. And the next piece was, as we deal with multi-tenant SaaS-based platform, we have quite a lot of customers, and we need to provide an isolation, customer isolation, so that the data is their data and their users are secured within QuickSight. On the top of the screen, you can see namespaces. QuickSight offers this feature called namespace. Namespace lets us to isolate users, data sets. A user in one namespace can't interact or share data with other user in another namespace. So with that, we were able to create multiple customer footprints in each namespaces. The next piece that I wanted to talk about was customizing the analysis. Users would need, we have analysis created in our in Workhuman platform. So those analysis needs to be shared with our customers because it's not going to be changing much drastically, but it gives them a starting point to start with. So how can we replicate that analysis into each customer's data namespaces? We did this through QuickSight API and copying the templates using the QuickSight API in each customer's data sets, namespace, and binded them with customer-specific data sets. Lastly, customers wanted to manage their security. So that is, within the solution, for example, if an analysis is published, they wanted a subset of users to be limited to see what data points they are authorized to see. QuickSight has row-level security, but from our point of view, we call that as a limiting criteria in our platform. We allowed users to create their own set of rules within our user interface, and then that gets translated back to row-level security in QuickSight. And what that means is now it allows the customers to manage who can see what in their control rather than us getting involved. So it's a pure self-service way of delivering capabilities into the hands of the customer rather than asking us, Workhuman, to do the infrastructure or the security rules changes. The integration of this embedded dashboard is a game changer for us because we are able to launch multiple dashboards, multiple customers at scale. We have thousands of users using this approach now. We achieved this without need for any infrastructure. And the management seamlessly accommodated thousands of users. So, closing note, I just wanted to give you a sense of how we were able to do this. We heavily relied upon our data platform to deliver these capabilities. So, it's important to get the foundation blocks right in place so that you can pivot as the data needs change in the future. I would like to thank AWS and the team to give me the opportunity to speak at reInvent. And with that, I'll pass back to Sandy. Thanks.
Thank you, Kamal. Two things I want you to take away from this. First one is data API service was The beauty of that kind of architecture is that you can cater to customers who are not in AWS cloud. Right? Not all of your customers would be in AWS. A data API service can transfer the data over secure HTTP calls. Right? The second, with QuickSight, you think about scaling to multiple customers just from one QuickSight account and embedding that experience in your product. Talk about efficiency and building these multi-tenant application architectures within your BI service is a game changer. I would love you to explore more when you leave this session on those topics. Now, before we close the session, I wanted to give you some thoughts on serverless services, how to think about performance optimization with serverless services. Because with serverless, we are extracting away a lot of responsibility from your side. So we are managing security, scalability, availability, infrastructure management, patching, et cetera, right? So what do you do about performance, right? Firstly, selection, right? So you think about, so right now in the data and analytics space, we have got a serverless service in each of the capabilities. Tied back to the architecture diagram I shared in the beginning, the different components, the different areas. Ingestion, we have got a serverless service. For processing, we have got one. For storage, data warehousing, search and analytics, visualization, governance, metadata management, we have got a serverless offering in each of these areas. Now, what you need to do is apply this performance optimization wheel on your data workloads. The first step is the selection process. Can you take a serverless first strategy? Does serverless fit in your workloads, keeping in mind the pentagon, the balance between all of those factors? Choose purpose-built services. Don't go for one-size-fits-all. That leads to bottlenecks. And once you have made selections, also think about the review process. How do you do reviews in an ongoing basis? We provide the AWS Trusted Advisor and AWS well-architected framework to help you review your workloads in an ongoing basis. This is not a one-time job. You have to do it. And we recommend, for example, with AWS well-architected framework, run it every 6 months. The account essays of the AWS solution architects can help you run these reviews. Third, trade-offs. We'd already talked about it, right? How do you implement caching against compression? How do you agree on service-level agreements with your consumers? What kind of trade-offs can you make to make your system more efficient and more performant? Think about that. Use that pentagon model to think about that. And then obviously monitoring, observability, doing the baselining of the data. Where are you today? How can you optimize performance? Once you have done that, where are you at that point? How can you optimize further? This is an ongoing process, ladies and gentlemen. It is called continuous improvement. And you have to apply this wheel to think about these factors when you put the performance lens on your data systems. And how can we help? And what you can do next? So if you are starting blank, like you don't have a data system you want to design from the beginning, we can align on the data strategy. We have got a data-driven everything program where data strategies can align with your organizations and help you build that data strategy. Do a pilot with one use case, build that underlying framework so that you can onboard other use cases on top of it. Second, modernization and migration. If you want to move off on-premises, modernize your data architecture, move to serverless. The Reimagined Data Program aligns specialists from AWS with your account teams to help you plan for migration and modernization. And thirdly, the AWS well-architected framework. It has got 6 pillars around cost optimization, security, performance, sustainability, right? So what I want you to do is see how you can run these reviews, plan for those reviews, talk to your account manager and account solution architect to see how you can optimize with those lenses on your data systems. With that, ladies and gentlemen, one last request. Please leave us some reviews on our content. We spent a lot of time on creating this content. If you leave some reviews, it helps us to bring this kind of content back in reInvent. Thank you very much for joining this session. I wish you all have a wonderful reInvent.